Okay, let's continue the second chapter. And in this video, I will start with another concept here. We talked about pattern. Now let's talk about process. What is a process? Any mechanism that causes a system to change its state, potentially generating characteristic patterns, which means that a process could lead to patterns, potentially generating characteristic patterns. So according to this definition, it seems like that process is the reason or is the origin of patterns, but their relationship is not that simple, okay? And pattern and process, what's the relationship between them? Patterns are the outcomes of processes, but patterns also can surprise or amplify those same processes. Okay, here is an example. We're going to talk about pattern and process, the relationship between transportation and urban form. Here, let's consider transportation as the process. Because when we're talking about transportation, it's usually, let's focus on the movement side of transportation, because transportation could be about the movement of entities, could be about the masses of transportation, could be about the infrastructure of transportation. Now let's consider movement only. Let's only talk about the movement side of transportation. So here, transportation is a process, and urban form is pattern. So before Industrial Revolution, right, we have city centers like this. It's an orange circle because back then we can only walk. You cannot walk very far away and get back home to have food and sleep, right? So back then, a town is usually very small, just like this. And we also had horse car as the only transportation method, which means that we can move to further places, but not very far away. So back then, the CBD, if there was CBD, okay, but let's call it CBD. CBD was a little bit larger than the town itself. Or more accurately, when you are using a horse car, you can move further than walking, right? So here we have the pattern led by a specific transportation method or a transportation movement. If the movement is walking, right, the pattern is here. It's a small circle. That's the shape of the town. And if you have a horse car, you can go to further places and the pattern changed due to the change of movement, because now you can move by a horse car instead of by your legs. So the pattern changed, right? So this is a result of what? Of the change of process. And the process here is movement, is transportation. And then we have streetcar. You can consider a streetcar is a small train, okay, powered by steam engine, but not that powerful, not like trains today can transport tons of items. It's not possible back then. But yeah, since the transportation, the way of movement changed, the process changed, the pattern also changed. You can say that the shape of this town, the shape of CBD, I mean, the shape of the town didn't change. It's still this this orange circle, because we still define this town covers an area that you can walk. You can only walk to. And since now we have streetcar, we have rails. Connecting different towns, right? We have suburb towns, right? Each suburb town is represented by a black dot here. So here the spatial pattern of these tongues changed because of the change from the process, because the change of transportation, right? So here we have a star shape, big city, big town, and small towns or suburb towns. They are connected to this huge town by railways. And then we have bicycle. We have bicycle. We can choose to walk. We can choose to walk, or we can use another method, maybe still horse car, or you can just take a streetcar to further places to form. So walking and streetcar, they formed this pattern here, right? This pattern here. So the star shape CBD area is still here. Big town and small towns, they are still connected by streetcars. But now since we can use bicycle, we have roads, right? The process changed again, or you can say new method of movement, which is bicycle, has been added to the process. So the shape of this area, metropolitan area, also changed. The pattern also changed. Now, because we have roads, we have something called suburb, right? You can ride a bicycle to the town to work during the day and use the road to go back to your home in suburb. Okay, and then we have automobile. Obviously, the road network becomes even more complex, which means that the process has changed again. The transportation changed again. And today we have a pattern like this. This is a metropolitan area, a very typical pattern for a metropolitan area today. We have a central area, which is usually the downtown area of the metropolitan. And we have several small satellite cities. They are in they're in orange. And we have other small suburb towns. They are represented by black dots. And we have huge suburb area. And since the city is expanding, we have highways connecting different roads that are surrounding the city. And these highways, this road network, they form the skeleton of the city. And when the city is expanding, we have more and more new suburb areas. So you can see here, transportation is a process. Urban form, urban shape is the pattern. So since the transportation, the method of movement evolves, the pattern changes accordingly as the result of this change of method of movement. But on the other hand, today, this is the pattern we want. So today, urban form decides the development of transportation. When you're trying to create or to construct new roads, to expand your metropolitan area, you choose to follow this pattern. And since the pattern has been decided, right, your road, your transportation infrastructure will have to follow this pattern to change accordingly. Right? So this is a relationship between transportation and urban form. Or it's an example to address the relationship between pattern and process. Pattern is the result of processes. And sometimes pattern can amplify or surprise processes. Okay, so that's the relationship. Next, let's talk about scale. Scale compared to patterns and processes is a more complex concept because it has multiple meanings, and in different contexts, someone may be talking, maybe using one of these concepts of scale, and you should be able to differentiate it. Okay, so multiple meanings for scale. Firstly, cartography scale is a ratio between map distance and corresponding real distance. Usually it is addressed by a scale bar in a map, right? And the second second meaning of scale here is called analysis scale, size of units in which phenomena are measured or the extent of the area of interest. For example, meter can be considered as a scale or a unit, right? Or kilometer or square kilometer as a unit, as a scale for area, right? The third meaning of scale, or the third definition of scale, is called phenomenon scale, the size at which geographic structures exist. For example, a hurricane. A hurricane is happening at a scale of what? Of several states, because usually if there is a hurricane, for example, Katrina, it was a disaster. It covers several states of United States, of US, right? So the size at which these geographic structures exist is what? Is maybe hundreds, thousands of square miles or square kilometers. So it was happening at what? At state level, at state scale. And we also have something called spatial scale. And a spatial scale. A spatial scale is affected by two factors. First one, grain, or it has another word, it's called resolution. Refers to the smallest entities that can be distinguished. If you know remote sensing, you should know that there is something called spatial resolution in remote sensing imagery. It represents the real world area that is addressed by a single pixel in your remote sensing image. For example, if the spatial resolution of a remote sensing image is 30 meters, it means that each pixel in that remote sensing image represents a 30 by 30 meter real world area. Okay, so 30 meter is called resolution, or you can say that 30 meter is the grain of that image. Okay, and another factor affects spatial scale is called extent, the size of the study area. This is very similar to the phenomenon scale I mentioned before. If you are doing research about Hurricane Katrina, your extent, your size of the study area should be at state level, right? So extent for the spatial scale of Katrina study should be what? Should be at state level, or sometimes we simply call it state scale. Okay, and here is an example showing the relationship between grain and the information provided. Okay, for example, we have three remote sensing images. The first one, the resolution, the grain is 4 kilometer, then 1 kilometer. Obviously, this is finer. And the last one is even finer, is 270 meter. So it means that, okay, in the first image, we have a lot of small patches here. Each patch represents a 4 kilometer by 4 kilometer real world area. For example, this green patch here is not too obvious. Let's talk about this dark yellow area here. It's a 4 kilometer by 4 kilometer real world area. Okay. Similarly, we have 1 kilometer and 270 meter, 270 meter spatial resolution. So the difference is that if you compare the 4 kilometer image and 1 kilometer image, obviously each pixel can provide more information. Okay, from the second image compared to the first image, because a pixel is the smallest unit in a remote sensing image. So if if a pixel covers 4 by 4 kilometer area in the real world, then this pixel has a single value. For example, the abundance of vegetation for that huge area because it's 4 kilometer by 4 kilometer. But if the grain is becoming finer, each pixel only covers 1 by 1 kilometer area in the real world, then we have more information for the specific area because this huge square here only has one value for vegetation abundance. But this area is covered by maybe it's 4 by 4, right? Then this area is covered by 4 pixels in this image with finer resolution, which means we have 4 values for vegetation abundance for the same area because we have 4 pixels covering the same area in the first image. Similarly, if you are going to increase the spatial resolution continuously to make it 270 meter by 270 meter for a single pixel, you will get more detailed information for the same area, right? So in summary, the higher the resolution, the higher the spatial resolution, the more detailed information you can get from the same area when we're talking about raster data, when we're talking about remote sensing image, or in any other application using any other tools, as long as we're talking about spatial scale in GIS, in geography. Okay, so spatial scale might be the most important concept here compared to the other three. But you should also know that there is cartography scale, analysis scale, phenomenon scale. And when some people is talking about scale, you should say, okay, stop. Firstly, please provide the definition, the type of scale you are talking about. Are you talking about cartography scale, analysis scale, phenomenon scale, or research scale, or spatial scale? Right? It's complex. And scale can be tricky because there is scale dependence. What does it mean? It means that patterns, they are a function of scale. As scale changes, the observed or simulated patterns may change. This applies to most but not all spatial phenomena. What does it mean? It means that the choosing of scale is important to your research because even you're looking at the same area, you're looking at the same phenomenon that is happening in this area. When you choose different scales, the pattern you will find could vary because the scale changed. Okay, so that's called scale dependence. That's called scale dependence. For example, here, we have this blue area with a lot of dots inside. So we have learned 4 types of null models. Which one does this belong to? I would say random, right? Because there is no obvious clustering here, and there is no obvious empty space within this area. So at this scale, obviously, the pattern is random. But if I'm telling you this is only a part of a larger space, and this time our research scale is not at this blue area level, we're zooming out. And when we're zooming out, this blue area is only a part of the big picture. Obviously, the scale changed. And this time, can you say the pattern here for the blue area is still random? No, it's not. It's clustered because there are so many dots within this huge space, but most of them, they are clustered within this small blue area. So scale changed from left to right. And your conclusion about pattern also needs to change. It's not random anymore. It's clustered. Okay, so this is pretty important. And here is another example. I'm not going to go in detail, but the idea is the same. In figure A, we use 81 by 81 cells, or say pixels, to address a specific area using different grayscales. We have a pattern here. I would say random. Okay, I would say random. But again, if you make this green cursor, we use 21 by 21 pixels. This is the image you have. Obviously, less information, less details compared to figure A, but I would say the pattern stays the same. And then you make it even closer. Now it's 9 by 9 pixels or 9 by 9 cells. And you can say, yeah, here, I would say there is clustering, the black area here and the black area here. But this clustering in the first image is not that obvious, right? It means that when you change this, change the spatial resolution of the same area, I mean, your conclusion about pattern should also change. And you can also consider this change from A to B to C is a process of changing scale. For example, A, you are looking at a specific city, your research area is this city itself. So the spatial resolution here is pretty high. And B, you can consider that you are doing a research at county level. Since you are working at a higher level, it's not necessary to provide detailed information about this city anymore. So the spatial resolution is lower because now you're working at a county level. So yeah, that's it. And if you zoom out continuously, and now you're working at state or even country level, this whole city is represented now by only what? 9 by 9 cells. It used to be 81 by 81 cells. When you zoom out, the whole area is just represented by 9 by 9, which is 81 cells. So the scale changed, the pattern also changed. Okay. But there are some shapes, some patterns, they do not change, even the scale changes. This phenomenon is called scale invariance. Okay, it's not scale dependence, it's called scale invariance. So these shapes, they are called fractals. Fractals and fractal-like objects, they are scale invariant. It means that no matter how scale changes, the pattern of them does not change. In mathematics, a fractal is a detailed, recursive, and indefinitely self-similar mathematical set who has the same or similar morphology at all scales. If we translate the last part of the sentence to geographic language, it's called it should be who has the same or similar pattern at all scales, which means the pattern doesn't change, even the scale changes. Okay, typical fractals including Sierpinski Triangle, Koch snowflake, Pinot curve. You can look up these words, this phrase online, you will see them. Okay, and fractal-like objects in geography, river networks, coastlines, mountains, urban morphology, which means when you are looking at this group of geographic entities or phenomena, you should know that no matter how you zoom in or zoom out, the pattern doesn't change. Why? I'm going to give you examples. So here is a very simple example for Sierpinski triangle. Okay, so at the how to form a Sierpinski triangle. At the very beginning, it's just a black triangle. Then you create another white triangle inside this black triangle, huge one, right? Now we have 1, 2, 3, 4 triangles. And then you repeat this process, create more and more small white triangles inside each black triangles, and you can do this indefinitely. You can continue to do this until the end of the Earth, as long as you can zoom in continuously. So at the end, let's just say we have this very complex but simultaneously simple object here, Sierpinski Triangle. So when you're looking at it, no matter you zoom in or zoom out, the pattern doesn't change. It's always a triangle. It's black or white. Or there is another white triangle inside a black triangle. So imagine you zoom in. You are looking at this triangle, this object. You zoom in, you zoom out. You always see this pattern. It will not change. But when you zoom in or you zoom out, the scale changed, but the pattern doesn't change. Okay. Some examples here. For example, urban settlement patterns. Here is a town of I don't know the name. It's a town of France. Of France. You can see the dark area. They're more urbanized. The area with lighter grayscale, they are less urbanized. So this is a pattern for a specific city in terms of urbanization. So this pattern is here, right? We have clustered in downtown areas. They are highly urbanized, and this highly urbanized area is radiating to all directions, Maybe for this city to this direction and that direction to the northeast, and this direction to the southwest. But yeah, we have a center here, and the whole city is expanding based on this center, this downtown area. This is at city level. But if you zoom out, okay, this time we're looking at the whole Europe. And you can see the pattern here is the same, is similar. We have multiple small centers. And other urbanized areas, they're less urbanized, but they're surrounding these huge cities, these huge clusters. If you compare these two images, they are showing the urbanized area, spatial pattern of urbanized areas at different levels, different scales, city scale and continental scale. But the pattern doesn't change, right? So you can consider this as a fractal object. The spatial pattern of urbanized area is a fractal object. And similarly, let's talk about other fractal objects in nature. This image is showing the watershed. So we have huge rivers and small rivers. Let me say, geomorphology, right? Watershed or ridge, I would say it's a mountainous area, and different colors they are for different elevations. So we have mountain range, we have mountain ranges and small mountains. But no matter, we have this spatial pattern. But if you zoom in or zoom out, the pattern will stay the same. There is always a mainstream. You can consider this a mainstream or a larger range. It doesn't matter. And there are branches from the mainstream. There is always branches from the mainstream. And the third one, this is a picture of shoreline. You can see that the shape of this shoreline is very complex, highly convoluted, very complex. But no matter you're looking at this shoreline from this picture, or if you zoom in, a specific shoreline here will be zoomed in, but you will see another very complex, convoluted shoreline in a zoomed in picture, which means that the spatial pattern, this very complex shape of the shoreline will not change no matter you zoom in or zoom out. Okay, so pattern is, I would not say pattern is complex. I would say scale is complex, because when scale changes, it will lead to some changes in pattern, but sometimes the pattern never changes, even you change the scale. Okay. And scale and inference. Inference is a conclusion reached on the basis of evidence of and reasoning, and modeling is a type of inference. When we are dealing with scale, we should be very careful with our inference. Okay, there are types of inferential error made when transferring information across scales. We have three types of fallacy. The first type is called individualistic fallacy, which means that you draw a conclusion for the group based on the conclusion of an individual. The second type of error is called ecological fallacy. It's the opposite of the first fallacy. You draw a conclusion about an individual based on the conclusion from the group. And the third type of fallacy is called cross-level fallacy. It means that there could be error when you draw a conclusion for group B based on the conclusion from group A. Okay, like I said, scale is a tricky thing, and when you are transferring information from one scale to another, you should be careful, and there are typical errors you could make. Okay, and for examples, I will leave them as the start of the next video. Okay, thank you.